Okay, shuttle performance is great. Shuttle's done everything it was designed to do, and probably a few more things we didn't think of at the time. It's put military devices in orbit, commercial devices in orbit, scientific payloads, all to LEO, with solids that we brought along. It's taken stuff to the geosynchronous orbits. It's retrieved and replaced satellites. It's retrieved satellites and brought them down to the ground, repaired them, brought them back into orbit. It's repaired satellites in orbit, and it's launched elements of the space station. In the 1980s, the shuttle had only 4% of all the launches in the country, but it carried 41% of the mass launched. Shuttle R&D was well within what Nixon and Fletcher agreed to, the $5.2 billion plus 20% in 1970 dollars. And I mean quite a lot of, probably the 20% was only about 5 to 10% of that was actually used in that. In that sense, they overran what the OMB said we were to develop it for, where they didn't give us the 20% reserve. We overran it by 5 or 10%. Missed two key design issues. Call them system engineering issues. Cold O-rings, Challenger. We had O-rings in that vehicle, which when they were cold, they lost their flexibility. And when they were cold, in a design that was opened a little bit when the pressure came on internally, that was a disaster waiting to happen. So that was a bad design of the way the O-rings were designed into the vehicle. Second one is the foam shedding. We knew that we were going to have ice and or foam on that tank. And we really pressed the industry to make sure that that foam was going to stay on. We had foam enough that we didn't get a lot of icing, but we had foam that had to stay on because we knew that as it shed, we didn't think of so much of the carbon-carbon as the tiles, these brittle tiles that we had on the bottom of the shuttle. So foam shedding was known to be a problem all the way through design and development, but just has not been able to be solved. And after the Columbia accident, the Martin Company, I assume, worked for 2 years trying to make that foam stick better. And it did stick better, but pieces still came off. So the fleet has been grounded, and they got to get that fixed. And of course, we missed the operations cost. Two-stage reusable vehicle would have missed worse. I'm sure of that, because of the size of that first stage booster and the Mach numbers it had to go to. I guess I have concluded that spacecraft are not like airplanes. Every flight is a structural dive demonstration. You know, you develop an airplane and you fly it many times before you fly it to the corner of the VG diagram. And I can only think of one exception. A guy named Wheaties Welch, one of the greatest test pilots North America ever had, flew the first flight of the F-86, which is the fancy new jet that we brought in just before the Korean War. And on his first flight, it flew so well that he took it into a little dive, and the Mach meter went up to 1. And actually the ground data showed that he probably went to 1.04. Some say they heard a sonic boom. I'm not sure of that. But that was about a month before the X-1 went supersonic. So he did that. In those days, test pilots were kind of innovative, and they did things that they were told not to do, and he did it. But every flight's a structural dive demonstration. We go right up to max Q every time we fly. We go through wind shears that take it up to high Gs. We go to high Gs on the way up. We go to high Gs on the way down. We go max thermal every flight. So we're dealing with a tough set of activities when we do this. No reusable space system ever gets the millions of hours of stressed operation that airplanes get. Once an airplane gets through development, starts getting millions of hours of test data or information, where if you have a problem, you fix it. And you just don't get that in these systems. No reusable space system has decades of evolutionary model development. In other words, the airplane business has been so dramatically economical that you could build new airplanes every 10 years or so. And each new airplane took advantage of all the things known from the past airplane and designed into it. And as I said, every reusable system is exposed to enormous environmental variations every time. Thermal, vibration, pressure, Mach number, all these things happen every time. And so I look at the shuttle as being an amazing piece of machinery which is done extremely well in what I consider a continuing R&D environment. We just don't have yet an operational system. So, my view of the next program, keep it simple. It's sort of been a prime view that I've had of design ever since I've been in the airplane business. Don't stretch the technology. Use really good margins of safety, because we're dealing here with, as I said, maximum conditions on every flight. You better play it safe. Keep it small. Carry as few passengers as possible. Carry people or cargo, but not both. Keep the requirements to a minimum. Use as many past components and systems as have been proven to be reliable. Design for operations, very important. Design for operations. Easy access. One man can replace a black box. You don't have to run a big pickup truck out, a pickup machine to go take something out of it. And keep the design reserved while you're designing it, so that when operational issues come up, you can design for the operational issue and keep reducing the cost of operations. I don't know what all that means. I think it means that if we had it to do over again, it would have been great to be able to contain the requirements within NASA, probably build a much smaller system that you could get many more test flights at lower cost, and but we didn't have that opportunity, as you now know. So we have the shuttle disappearing into the distance. Decision has been made that the shuttle will be phased out in 2010, and it's going to be a tough issue, because now the shuttle is down in between flights because we lost foam on the last flight. They grounded the fleet till we can figure out what to do about that foam problem. And then the Hurricane Katrina knocked off the top of the VAB, which isn't a big deal, but it really messed up some of the tank facilities and tank access, and people's lives have been affected with losses of homes. And so there's a whole bunch of new issues involved in the shuttle that I read in the paper this morning may mean another delay in the next launch of the shuttle, and that means a compression of the time between now and 2010, when they're trying to use the shuttle to meet the commitments that we have with the Europeans and the Japanese about putting pieces of space station up into space. So an interesting new problem for the shuttle. Okay?
What went into the design of the shuttle, and I think what Dale alluded to at the end is very much to the point, and we'll be talking about this with the people when they talk about the individual systems, that in terms of the actual performance which we've gotten out of the shuttle, despite the fact that we have had 2 catastrophic accidents, which, by the way, involved not only the design of the shuttle, but the way we operated the shuttle, and that's an important thing that we'll spend time talking about. Had we not made the decision to launch Challenger on that cold day, we you know, who knows what would have happened. And similarly, we accepted the fact that foam was continually falling off of the tank, even though that was incompatible with the design specifications on the thermal insulation for the shuttle. So we had basically two parts of the shuttle system, and we had design incompatibilities, but we chose to keep on flying. But as a whole, the shuttle has been remarkably successful from a technical point of view in terms of what we have been able to do in near-Earth space has been, I think, you know, compared to what you could do working out of an Apollo capsule was absolutely phenomenal. And in fact, it will, you know, I think in terms of near-Earth operations, the shuttle will be sorely missed when we retire it. And there will be a lot of capabilities that we will be giving up. But on the other hand, where we really got it wrong by orders of magnitude was in the cost and reusability of the shuttle. Now perhaps that goes back to the requirements, because again, we were trying to do an awful lot of things for the very first time, and yet we were being told by the Office of Management and Budget that, you know, you said it had to be cost effective. I mean, in a sense, NASA was being asked to operate the shuttle almost as a commercial enterprise and to make money on it. So, you know, this is like you build a test vehicle for the first time, and you're being asked at the same time to operate it at a profit. And, you know, as you know, one of the systems engineering principles is you have this triangle. That's not working very well. I'm sure you've all seen this. Oh boy. All right. Performance, cost, schedule. You've all seen the triangle, right? And you can't specify all three. They are not all independent parameters. If you specify the performance, and then you're limiting the cost, you can't control the schedule. Anyway, all three of those we, in a sense, got specified when we accepted the requirements to build the shuttle. And something has to give, and in the end, it was the schedule and the cost. And we'll have more to say about this in the next couple of lectures. Okay, let's move into the question and answer period, and there have been a lot of material presented, and this is your chance to ask the guy who was here when it all happened. Go ahead. Dale, why don't you take center stage now?